Good morning, sunshine.
Hello, everyone. Sorry I'm a little late. Good news is I'll let y'all out ever early anyway, so that'll be kind of nice.
Oh, did you
Uh,
get new glasses?
yeah, these are ones. These are actually my prescription glasses. These are the ones I normally wear, are just like readers because I'm old. So yeah, these are my Oakley prescription, and I got some Tommy Hilfiger, as they call it, other prescription glasses that I bought. I decided once and for all to buy some really nice frames. That was my first pair of eyeglasses, really. I bought two really nice pairs of frames, and I've just used them repeatedly. That's these Oakleys and the Tommy Hilfiger.
I'm gonna
Yeah.
stop you there. Not everybody who wears glasses is getting old. We're just well read.
That's it.
Come
Well,
on.
I wear glasses and I'm like 21. What are you saying?
I
I've
know.
had glasses
well,
since
just
middle
rub it in,
school.
why don't you, Rosie? Jesus, me, 21. Oh God.
Oh god, yeah, no, I'm like bending over and just like, I've got my cane and everything. I should be in retirement by now.
Seriously, we're just
Yeah,
well
it
read.
just. I've always had wonderful eyesight, literally until I had my eye surgery, and ever since then it's been kind of. I mean, my eye surgery, my shoulder replacement surgery. I woke up. I actually, my blood pressure got really high, and it actually damaged my back part of my eyeball.
Oh
That
And
just,
wow.
that's what I noticed. I had something going on with my vision, and they found astigmatism.
that just tells
And
you
shortly
how
thereafter, I started
fragile
getting
our eyeballs are.
presbyopia.
Yeah. No,
Not fun.
I've had astigmatism since I was like 10, so
It's terrible. I can't stand living like this. I mean,
I want to get it fixed. Like I want to go in for surgery, but at the same time I'm like, ew, I have to be awake during that? No, thank you.
yeah, it's kind of creepy, ain't it? Well, I've known a lot of people that had it and swore by it. Now I'm going to have it just as soon as I can spare the time and finances, at least to get rid of the stigmatism. But that's not going to help my nearsightedness. So that's a whole other problem. I've actually always read like this, not because I was blind, but just because I don't know. I just did it for, I don't know if it was attention span or what, because I certainly got some ADD issues going on. Uh, I wanted to let you guys know that I did finally post the questions about the movie. I sent a link to. I called it The History of Earth, but that's all. That's what the YouTube channel, or the YouTube page that had the video link on it. That's what it called it. It's not The History of the Earth, which is another movie, which I just bought, by the way. I actually bought both of these. The movie that you're actually watching, if you haven't already, it's called Earth: Making of a Planet. And I hate the narrator's voice. He just sounds like, "So I took a poop." You know, it's talking really excitedly about the most mundane things. But anyways, it's still a great movie, and I took it looks like about 8, 9 pages of notes when I was making up your questions. So I've now posted those questions in there. I think it's 12 questions total, but they're not trivial. So I wanted to give you a little bit of time from today's class to work on that in addition to your lab time. Just because, like I said, it took me, I ended up watching it for about 3.5, 4 hours to take my notes, and then spend another 30, 45 minutes writing the questions. So I know
Give
it
us
can.
some time. Post your notes.
Probably not, because that gives a lot of the answers. But it was entertaining. I mean, when you take an hour and 34-minute movie and make it into a whole, uh, you know, 3 hour watching fest, you can learn a lot.
You're gonna have to make me climb back through my geology notes and pull out the movie notes again.
Yeah, well, that's sort of the cool part about this is, or actually, I should say, this is the bad part about it as well as the cool part. They mention so many things, so many different species, so many different things happening, but they mention them. That's the disadvantage of watching TV or listening to a radio, or even listening to a recording. You have a hard time figuring out which word they were using. So I took the time to actually track down the words they used. So one of the first species they talk about was I think he called it a armored slug. And I could have sworn he said Rywaxia, like Rywaxii, but it's actually Wiwaxia.
Wiwaxia.
Yeah. So I tracked down all those names, Amalosaurs and all that. And what was the other one? Anomalous Carsid or Anomalous Sarkid or something like that. I
I just
tracked
want to
down all
keep
those.
hearing you try to pronounce it.
Yeah. So, anyways, I did want to go ahead and put those in the actual questions because I want you to sort of enjoy the same thing I did, which was looking at those individual species, taking what the video said was important about them, but also putting them in a place in the eon era and period of geologic time or evolutionary time. So that's why the questions are so involved. That's why I'm giving you so much time to do it. The other thing I want to talk about today, first off, does anybody have any questions before I get too far ahead of myself?
Too late.
Yeah, no questions about past material. So all the chapters should be linked. Where we just finished chapter 17, we're going into chapter 18, and that's what I'm going to talk about just a little bit today. I'm going to give you sort of the intro to the theory of relativity, the special theory of relativity, and I'll give you a little bit of a story about the general theory of relativity as well.
Quick question. When are you popping the practice tests for the next test?
The next test, if I remember correctly, I think I found out. I think I found out. What was the last test on? Do you recall what chapters?
14, 15, I think.
It was
Okay.
13 and 14.
13, 14. Yeah,
So the next should be 15 and 16.
which should be open.
Yeah, let me see if I got it made already. I think I did make it. If I did, let me go ahead and open it right now while I've got you here, so I don't forget. Yes, I do have that made. That's right. So it's now open, and let me test it real quick to see if it actually works. Because sometimes it's a test, but it doesn't really work because it's the question banks didn't come over or something weird like that. Let's see. It looks like it has, yes, 10 questions, and all of them appear to be working. So go back here. I'm going to say save. So it is now available, and I got to moderate it. That's the process you go through by letting people have extra time so that they can, if they have an accommodation or anything. So I've been doing that lately because I'm, a super instructor. Yeah, that's my story.
You stick to that.
Yes. Oh, there's another person that has accommodation, so I'll give them that time too. And then there's a third. Who the heck is a third? Oh, I know who it is. Oh my God. Oh, there they are. So there's an accommodation for all three of my accommodated students this time, and it is now available. So the practice test is now available for you folks. That is on 15 and 16. If you, hopefully you've already done the homeworks for 15 and 16, but certainly you can start doing the practice test now. And of course, don't forget chapter 17 homework has been posted. Chapter 18 homework's been posted as well, but not on Canvas, just on SmartWork. So, well, now that I've got that practice test out there, let me go ahead and get started on the special theory of relativity. So Maxwell had this sort of terrible life that I've mentioned to you guys in a couple different instances. In that he was really brilliant and he did great things, and I'm sure mostly he would consider his life happy, but he still had a bit of a problem. The Cambridge University has a Wrangler test. So basically, you go through 4 years of college with, or however many years it takes or whatever, at Cambridge, and they didn't necessarily have a grade system. And they would have classes like you could take class A or whatever, and then you come into class and the person's going to lecture. He might even take time to assign some homework problems. You don't necessarily do that. He's not going to take them up. He's not going to test you necessarily. He's not going to do any of that kind of stuff. And then at the end of the 4 years, you have one ginormous test on everything. And as if that wasn't tough enough, they then take the results, grade them, and put them publicly with your first and last name on a list, and it's called the Wrangler list. And the person that got first is called the Wrangler, also called the first Wrangler. The person who got in second was the second Wrangler, and so on and so forth. Well, Maxwell did this, and he came in second. So he sort of had the ire of people, or he had people that basically didn't think he was that much of a big deal because he came in as second Wrangler instead of first Wrangler. For the record, the guy that got first Wrangler, we don't remember his name. So obviously he didn't do that much, but obviously Maxwell did. So he had this chip on his shoulder, or I should say more like had a target on his head, because I don't think he ever felt necessarily the chip on his shoulder about being second Wrangler. Maybe he did, maybe he didn't. All I know is he was hired as a location professor of mathematics at Cambridge, which is the same position held by Newton. And anybody that has a job that Newton used to have should be like, oh, yeah, I mean, other than Paperboy or whatever, they should be like, yeah, I did something pretty freaking awesome. So he had that position, and he did great things. I mean, he took all the experiments that people were doing, Faraday and Tesla and all these. Well, actually, not Tesla. Tesla was around after his death. But Faraday and Gauss and all these people, he took all their work and sort of put it all together and made a comprehensive idea out of everything. In fact, he was able to take all those findings that these experimental findings that these people have made and condense them down to 4 equations, and they're called Maxwell's equations, and they're 4 uh, differential equations in the language of vector calculus, which probably at the time maybe 100 people knew vector calculus in the whole planet. So it was sort of a very esoteric thing, but they were absolutely right, and they're still right. And we only need to make corrections for them in the quantum mechanical realm, and that's not very big of a difference. So we usually don't have to do that. Electrical engineers very seldom have to use QED instead of Maxwell's equations, to give you some idea of how valid his equations are. But because it was in this sort of esoteric language, a lot of people use that as yet another reason to just ignore him, because I'm not going to take the time to learn a whole branch of mathematics just so I can do my work as a scientist. So that was sort of another down factor about him. And he ended up dying, I think, at the ripe old age of 43 of some horribly painful stomach cancer, just like his mother. But this was a terrible case. But he had, he actually come up with the statistics that we use to actually study how atoms and molecules behave. We still use it to this day. He came up with these 4 equations, which we still use to this day. He was the first person to explain what Saturn's rings were. So he was a brilliant man. But because of that, like I said, he died sort of without the respect of his peers. Kind of a bum situation. I think he died in let's say 1830s to 1860, somewhere in there. By the time Einstein comes along, everybody knows Maxwell's equations are on point and loves them. And of course, he's one of Einstein's famous heroes, if you will. So Einstein's looking at Maxwell's equations, and oddly enough, Maxwell's equations are relativistically correct, meaning they're already consistent with the special theory of relativity. It's almost like Maxwell uh, created special relativity before he actually created electricity and magnetism laws, or by creating the electricity and magnetism laws. So it's a really big deal in that they're consistent with it. So you don't have to change everything to make it match special relativity. But what Einstein did was he looked at those equations, and if you put the 4 together in a very specific way that you learn as an undergraduate in physics program or in an engineering program, you can get something called a wave equation. And a wave equation is something that every physicist and most good engineers know. A wave equation is whatever's doing the oscillating. You're going to have the second derivative of that with respect to position, and the second derivative of that with respect to time on opposite sides of an equal symbol. And then there's a slot for the square of the velocity of the wave. Okay. When you put that together, those 4 equations together, and get that wave equation for Maxwell's equations, you get the equations of the speed of light for the speed. And at that instant, of course, Maxwell knew, oh wow, I know what light is. It's this electric field oscillating in one plane, a magnetic field oscillating in a perpendicular plane, and a third perpendicular direction is the direction in which it goes according to the right hand rule. E cross B goes into V. So if you put your let's say you put your index finger in the direction of electric field, and you put your middle finger in like this in the direction of the magnetic field, then your thumb of your right hand automatically points in the direction that the wave is going. Okay. So that was the actual wave equation. And when Einstein looked at that wave equation, he realized that it didn't matter if you did that wave equation for me and you, who are sitting here perfectly still, or if you imagine a spaceship flying by the Earth at, let's say, 1% of the speed of light. If you wrote out the exact same equations for wave equation for that spacecraft, it wouldn't have any difference to account for the fact that its velocity had changed. In other words, the fact that reference frame has a velocity of 1% of the speed of light. And that caused a lot of what Einstein considered to be paradoxes, or what were paradoxes. Paradoxes are basically anytime 2 perfectly reasonable accepted theories are basically make a prediction that's mutually impossible. In other words, they're inconsistent with each other. And whenever you have that in a science, that science is not finished. It's sort of like picking a raw tomato or something. You can make a fried green tomato sandwich, and that would be good, but it pretty much sucks other than that. And that's the way science is. If you have a paradox in it, you're unfinished. So Einstein kept finding these paradoxes about, like riding a light beam and whether he could see his image in a mirror or not so he could shave. Because of that, he had to come up with a special theory of relativity. And people have said genius is the ability to hit a target that no one else can hit. But I heard a president of a college one time made a much smarter and I think more astute statement of what genius is. And he said genius is the ability to see a target that no one else saw. And that's what Einstein did. Einstein saw a problem with physics that no one saw. And not only did he see it, he solved it and did it before anybody really knew there was a problem. So it's really, really, really super impressive what Einstein did. That's why he normally ranks at the very top, maybe, usually even above Aristotle and various other great thinkers like Darwin and stuff like that. So it really is a remarkable thing that he did. And it did it in 1905 in a year where he made several publications. I think he had 6 or 7 publications in that year and probably could have won 3 or 4 Nobel Prizes from them. It was such a shoe in fact, that he was going to get a Nobel Prize that he used that as a bargaining ploy when him and his wife were breaking up. He didn't have any money to pay her off. So, for her staying home, she was a physicist too, but she had to take a break so she could stay home with kids and keep the house and that sort of stuff. So there should have been some kind of reckoning where he would take care of her. He didn't have the money. He was a lowly professor and wasn't really famous at this point. So he told her, if you let me go, I'll give you my Nobel Prize winnings. And she took it, and rightfully so, because she ended up getting the Nobel Prize winnings for that. So that was kind of neat. Anyways, what he did was he realized that 2 things had to be true. And these are the 2 principles of relativity. Your book talks about them. You can write them down from your book. The first one, the principle of relativity, is that the laws of physics are the same for all inertial observers. This is the first law or the first principle of the special theory of relativity. The laws of physics are the same for all inertial observers. Now, inertial observers is a little weird. What he means is everybody who sees Galileo's law of inertia or Newton's first law of motion, they're both called laws of inertia. If anybody finds that they're in a frame where that's valid, then special relativity applies to it because it's the laws of physics are the same for all inertial observers. But here's the weird part. Inertial observer means something very specific to Einstein here. Imagine taking a merry-go-round, like on a playground or something like that, and attaching a video camera to it from above, shining down or viewing downward, where you can only see the disc of the merry-go-round. So you can't tell if it's moving. It might be on the back of a truck, being carried off. It might be on the mounted on an axle in the middle of a park. It might be spinning. It might not be. You just don't know. But if you take a basketball and say stick it just a little bit, pretty close to center, but not exactly the center, if that thing's actually spinning, what you're going to see is that ball is just all of a sudden going to sort of shoot off to one side. And you don't physically see any force. You cannot observe a force that touched that ball and made it take off and accelerate. And that, of course, is not consistent with the law of inertia unless there was a force. Now, we would, say that force is a centrifugal force, which we actually told you is not a force at all. But the big deal is there is not an obvious force pushing it or pulling it. So it's not an inertial reference frame. Similarly, if you were just filming a ball that appeared to be floating in space, just a black background, and then all of a sudden you see the ball accelerate downward, you say, I don't see any forces acting on it, yet it sped up. It went, a distance of 5 meters in the first second, and it went a distance of 20 meters by the second. That's acceleration, and therefore it's a non-inertial reference frame. If you remember what we talked about on gravity, basically in the first second of falling, an object will fall 5 meters, and then the second it'll fall about 20 meters total, and in the third second it'll fall on about 45 meters total. That's acceleration due to gravity. But Einstein says, hey, we're taking gravity out of this because according to Newton, it's a force, but I'm not cool with that because forces can't act over distances unless they're physically touching something. So that's what he meant by the laws of physics are the same in all inertial for all inertial observers. The second principle of relativity was really the principle of the constancy of the speed of light. And it basically says it says that the speed of light is a constant independent of the motion of the source or the motion of the observer. So we're talking like someone riding on a Mack truck. So you take a Mack truck, you got a big flatbed on the back. Maybe it's the one for carrying logs or something like that, or trees. You're riding on the back of that Mack bed truck or that Mack flatbed truck, and the truck's going 60 miles per hour north, and you're facing north. And let's say you're old like me, so you only got about a 60 mile per hour fastball. So you throw a 60 mile per hour fastball north as well. If someone's on the side of the road and that ball comes at them, they would measure it with a radar gun, say going 120 miles per hour. Because if you imagine over a whole hour, if this motion was not disturbed, you would imagine the truck would travel 60 miles, but then the ball would travel an additional 60 miles on top of that. The total miles would be 120 miles. And of course, that was done over an hour, so the speed would be 120 miles per hour. If I threw in the backwards direction at 60, what you'd see is the truck would move a whole distance of 60 miles in 1 hour, while the ball moved a distance of 60 miles in 1 hour the opposite way, getting a net result of 0. And that's because I threw in the opposite direction, so the velocities actually subtract from one another. That's the way things behave. That's reality. We know that. In fact, we know, when they say a car is designed to withstand a head-on collision up to 30 miles per hour, that sounds horrible. Like, well, that's just crappy. No one gets in a wreck at 30 miles per hour. Well, there's several reasons why that's a goal. One, if you go much higher, it gets a lot more expensive to build a car that's safe, and the car gets a lot heavier, a lot less fuel efficient, all that sort of stuff. But the real reason is that one, you're going to slow down more than likely, unless you happen to have fallen asleep or passed out at the wheel. There's going to be some deceleration when you realize, oh crap, I'm getting ready to run head on into someone. But the other reason, and the more important one, I think, is that in reality, if it's a head-on collision, then the other person going 30 and you going 30 is equivalent to a 60 mile per hour collision. So that's also basically like a 60 mile per hour collision. So that's another way of thinking about it, is how those velocities add. So with light, things are different. If I, instead of throwing a baseball at 60 miles per hour, I shoot a photon of light, pretending that the speed of light is 60 miles per hour, then that would be unaffected at all. Okay. The velocity of the light that I sent out from the back of the Mac bed truck, even if the Mac bed truck is going 3/4 of the speed of light and I shoot out a light beam going the speed of light, okay, you on the side of the road would say the Mac truck's coming at me at 3/4 the speed of light, and you'd say Mr. Younger's light is coming at me at c, the speed of light, 300 million meters per second, or 300,000 kilometers per second. If the Mac truck sped up to 99.999% of the speed of light, and then I shot my flashlight at you, you would say, oh, wow, that Mac truck's going 99.999% of the speed of light. And this light that Mr. Younger shot, that's going the whole speed of light. Wow, that's impressive, right? Notice it didn't increase at all. So not only that, if you now say, okay, I'm going to run towards that 99.99% of the speed of light Mac truck, I'm going to get on my scooter and run towards that Mac truck like a head-on collision at 99.999% of the speed of light. And then Mr. Younger shoots a light beam at me, and lo and behold, I still measure that light beam to be moving at the speed of light, period. Okay, that is the weirdest part of the principle of special relativity, or the principle of the constancy of speed of light. The speed of light is always going to be the speed of light, no matter how fast the source is going, no matter how fast the observer is going towards the source or away from the source. It's always still going to be that speed of light in a vacuum. Now, the speed of light does change. Specifically, like if light goes from a vacuum where it's doing 299,458,752 meters per second, and then it enters the atmosphere, it's going to slow down by roughly a factor of, I think, 0.98 or something. It's really, really close. It's within a couple percent of the regular speed of light. So air slows it down, but that's now the speed of light in air. And that, of course, is the fastest thing in air. And if it goes in the water, it's going to slow down by a factor of about 1.3, or excuse me, 1.3. And if it goes in the glass, it's going to slow down by a factor of about 1.5. So it can slow down, but again, it's still the fastest thing in each of those media, but it's not going to change due to the motion of the source or the motion of the observer. Now, does that bother people? Does that seem weird to you guys?
Like, what do you mean in terms of weird?
Like, have you ever thought that anybody would ever tell you that fact and have you ask you to believe it?
No, I don't. I think this is definitely the first.
Yeah. So it's that kind of thing. It's really an anomaly, and that's the part of physics and mathematics that I like. That's what got me out of being the loser that graduated third from last in a class of about 60. Was something interesting that didn't seem obvious was in fact contradictory in my mind, turned out to be the absolute truth. In my case, it was if you try to rationalize the decimal 0.999 going on for infinity, that is a rational number. 0.999 for infinity is a rational number, which means it can be expressed by a ratio of two integers. When you do that rationalization process, you end up finding that the rationalization of 0.999999 forever is actually 1. So that was absurd to me because I know it's really, really close to 1, but it's definitely not 1. But it's a mathematical fact that the rationalization of 0.9 for infinity is really 1. So that's another thing that blew me away. Another thing, for instance, from quantum mechanics is there's a thing called a spinor, S-P-I-N-O-R, a spinor. It's a mathematical construct that comes in quite handy occasionally in quantum mechanics, but especially in general relativity. There's things you can use it for in there. But it's this weird thing that if you rotate it 180 degrees, nothing happens. But if you rotate it 360 degrees, then it's upside down. So that's some of the cool stuff that exists in the science world that you don't get exposed to in everyday life. But I think if more people saw weird stuff like that, they might be a little bit more interested in the sciences and mathematics. But this is one of them, the constancy of the speed of light. And remember, speed of light is the number of, let's say, miles per hour something travels. And if you fix that as a constant, that means the two things that make up the miles and the hours are going to change in weird ways, right? You've got to keep the ratio of miles traveled by hours. You've got to keep that ratio a constant. So if the distance goes up, then you've got to accommodate that by making the time go up. Or if the distance goes down, you got to accommodate that by making the time go down. So you can start to see that maybe if I force the speed of light to be a constant, that might just cause space to be jacked up, and it might just cause time to be jacked up. And that is absolutely the fact. Okay. One thing you can think of is, let's imagine these two spaceships, the green spaceship and the orange spaceship. The green spaceship is just sitting here. The orange one comes flying by. Maybe it's traveling at about 90% of the speed of light, some god awfully fast amount. And the instant they get exactly beside each other, meaning the tip is lined up with the tip and the back is lined up with the back, two lightning bolts are sent out. We send out one lightning bolt that strikes a piece of metal that's touching both fronts of the vehicle, of the spacecraft, and another lightning bolt at the same time that hits a piece of metal that's touching both spacecrafts at the back. Okay. That immediately causes, in both cases, a light in the front of the spacecraft and a light in the back of the spacecraft. That causes both of those lights to fire a beam of light towards the center of the spacecraft. Okay. So if we're looking at this guy, ignore this one that's flying by right now. If we're looking at this guy, what just happened was a lightning bolt hit here and here at the same time. It sent out a pulse of light moving at the speed of light, and it sent out a pulse of light moving at the speed of light. So dead center in the middle, the two beams of light hit each other or hit a detector. And the detector says, I got them at exactly the same time. Ergo, the lightning strikes were simultaneous. That makes sense, right? Because the light's going to be fired from here, and it took 0.00009 seconds to get there. It took 0.00009 seconds to get there. That's the center of the spacecraft. This is equidistant from the front and the back. Therefore, the two lightning bolts hit this vehicle at the same time. Now, that is a fact. We know that. That's exactly what happened. But according to this spacecraft right here, okay, according to this spacecraft, it's flying by now, and it hit, and then because the speed of light is not changed by it moving at 90% of the speed of light is still the same from this end as it is from this end, as it is when it's sitting still. So this spacecraft has something moving at the speed of light from the front end going this way, while it's moving this way at 9/10 of the speed of light. So it actually, the detector in the middle of this spacecraft says, oh, this front beam of light hit me first. And then, a few instants later, the second beam of light hit me. Ergo, the lightning struck the front of the craft before the back of the craft. You see that now what we call simultaneity is not absolute? The green spacecraft thought that the lightning bolts struck the two vehicles at the same instant, and they called it simultaneous. But because this spacecraft was moving towards the source, it actually had this beam moving at 70, or excuse me, the speed of light this way. At the same this time, this was moving at 90% of the speed of light. So it actually hit this front part first and then the back part. So it said the front lightning bolt struck first and the second lightning bolt struck in the back last. So that's the first thing we've lost. There's no concrete definition, no universal idea of simultaneity. So two things you think are simultaneous might not be simultaneous in another time frame, in another frame where it's moving with some velocity. Now, I like to use this example, but it doesn't really work. But let me give you an idea. So we clap because the right hand and our left hand gets at the same point at the same point in time, right? So that's a clap, right? But in principle, what that means is someone else might see me go like that, right? Not hear any noises. That is not exactly correct, but it's sort of an idea of what we're talking about. Simultaneity is no longer a done deal. Now, the problem with this is obviously it made a sound, so that's something we could detect. So we'd certainly see some difference there, and it's quite complicated to explain what the difference is. But I'll just tell you, anything that you think is simultaneous may not be simultaneous in another frame. The best example of which comes from something called the ladder, LADDER, and the barn paradox. Feel free to Google that. I might cover it in our next class. I'm not sure. That one gives you a good instance of simultaneity being questionable, okay, meaning different from one frame to another. And then there's another paradox, neither of which are paradoxes, because like I told you, paradoxes are not allowed in science. So the fact that we call them a paradox is just because we didn't understand relativity when they came out. But the other one, or I say we didn't, we did, because those problems were brought up immediately by brilliant scientists, and immediately brilliant scientists were put down because they didn't understand that aspect of relativity necessarily, or they used it as an arguing point to try to say how relativity doesn't work. So the other one's the twin paradox, which you probably heard of as well. I will tell you that the paradox is not that the two twins have different ages. That's the way a lot of non-scientific books present this twin paradox. The twin paradox is when one twin tries to claim to be the younger one and the other one also claims to be the younger twin. Okay, the fact that the two twins are not the same age, that's just a fact. That happens. It's nothing you can do about it, and it's a ramification of relativity. So we'll talk about that a little bit later as well. So that one thing, that non-absolute simultaneity, means there's no absolute time. There's no distinct way to say this is the correct way to measure time and all these other ways are wrong. It's not that at all. So that's part of the relativity idea. The time can be relative. Not only can it be relative in terms of being simultaneous, it can be relevant in times of intervals of time, or in the case of intervals of time. So for instance, let's say we got 100 million ice cream cones from, let's say, Dairy Queen. And we got them to make them exactly like they're supposed to according to their training. They weighed them and everything. Only this time they weighed them with a super accurate device that measures to 6 decimal places, so they know it was right on the money. And we took 100 of them and did an experiment to see how long it took for them, sitting in the exact same temperature situation. And every time you lay the ice cream cone, immediately after being made, it sits on the ground or on the table, say, and it's sitting there with the swirl of ice cream all the way down, and it melts until it's basically a sugar cone full of white milky water. Okay, and let's say we did that for 100 of them, and we found that 100 of them, the average time was exactly 10 minutes. Okay, now if we did that trial 10 more times, then we'd of course use up, instead of 100, we've used up 1,000 of them. If we did it 1,000 more times, we've used up 10,000 of them. We've got millions of them. But if we took the averages of all those big trials, the difference between, or what we call the standard deviation, if you will, of that trial of trials, that standard deviation is something called the standard error, and that's what we use in science, just to give you a statistical sidebar that has nothing to do with relativity. But if we did that and we found that we worked it down so perfectly that there was almost no error, meaning the error was like in the 3rd decimal place in seconds. Okay, so every ice cream cone now melts in 10 minutes plus or minus 0.0003 seconds. Okay, Now you take this ice cream cone and you teleport it to these two spacecrafts. Okay. This spacecraft is magic, so it's just hovering over the Earth. Okay. It's in a geostationary orbit over the North Pole. So yeah, it's defying gravity. So it's just sitting there, and we transport it instantaneously with another one to the orange spacecraft. This orange spacecraft, on the other hand, is traveling at 86.6 times percent of the speed of light. 86.6% of the speed of light. That happens to be the square root of 3/4, by the way. Okay, so the square root of 3/4 is 0.86604, I think, but we're going to say it's 86.6% of the speed of light. This one, on the other hand, is sitting still according to us. So as we watch this green spacecraft, we start timing its actual ice cream cone, and we see, wow, it does take exactly 10 minutes. And we do this experiment over and over and over again. We find it does exactly 10 minutes plus or minus 0.0003 seconds, just like we found when we did it before. Now, the other scenario is this spacecraft happened to be flying by at 86.6% of the speed of light when we send the ice cream to it. Now, they ignore the inertia issues that might come in, as Star Trek did, but the ice cream cone is now there, and we watch it with a telescope and time it. And lo and behold, when it gets further down in space, another 20 minutes later, we find out the ice cream cone is finally melted. And that's exact, okay? If you really are traveling 86.604 roughly percent of the speed of light, then the time dilation factor is exactly 2. Okay, so the 10-minute ice cream, when it was set aboard a spacecraft traveling at 86.6% of the speed of light, it took 20 minutes. That is time dilation, and that's one of the ramifications of special relativity. Moving clocks move more slowly, and that means all moving clocks. Anything you want to count as a clock. If you're this Olympic athlete that have got your heart rate set up so that no matter what small amount of exercise you do, walking around the house or cooking, your heart rate never changes from 60 beats per minute, or let's say 50 beats per minute, because you're a super athlete, right? That is a time unit, and therefore your clock will run slowly when you're traveling at 86.6% of the speed of light. And in fact, for your heart to do 50 beats that it normally did in 1 minute, it's now going to take 2 minutes to do 50 beats. So our life processes, all that stuff, are slowed down by motion. Now here's the part where relativity comes in. To this spacecraft, it says, hey, I was just sitting back here, way over here. I was just sitting back here, and this stupid spacecraft, the green one, started flying towards me at 86.6% of the speed of light. So in the orange pin's frame, the orange spacecraft frame, the green spacecraft is moving the opposite direction at 86.6% of the speed of light. And if it used a telescope, it'd say, oh, wow, I got an ice cream cone just like us. That's cool. And he watches it, and it would take 20 minutes for that ice cream cone to melt. Okay, that's the relative part of it. There's no absolute time. We already talked about that. Now there's also no absolute space, because absolute space or absolute motion is not a real thing. In other words, according to this guy, this spacecraft was moving to my right. According to this this orange spacecraft, the green spacecraft was moving to my left. Okay, both at the same speed but opposite in direction. So either one has a valid claim. Both of them are correct. The green pin is correct that the orange spacecraft took 20 minutes to melt the ice cream, and the orange spacecraft occupants are correct to say that the green pin occupants and ice cream cone took 20 minutes. So that's the first, or that's the second big thing that comes from special theory of relativity. Anybody have any questions on that?
Anybody want ice cream now?
I do. So, and that's part of the twin paradox. So the twin paradox would just be, let's imagine instead of sending an ice cream cone there, I leave one twin on Earth and the other twin gets teleported to the orange spacecraft. It flies to Alpha Centauri, which is about 4.2 light years away. So it's going to take, maybe 4.5 light years to actually get there, because, it's only going 86.6% of the speed of light instead of the whole speed of light. If it was going the whole speed of light, the time required for us to observe it making it to Alpha Centauri would be 4.2 years. I'm roughly approximating. What I really should do is take 4.2 and divide it by 0.866, and that would give me exactly how much time it would take the orange spacecraft traveling at 86.6% of the speed of light to get to Alpha Centauri. But then what's going to happen is that twin on the orange spacecraft is going to teleport back to another spacecraft, a blue spacecraft that happens to be traveling also at 86.6% of the speed of light. And it's going to come back, and it's going to take another 4.5 years to get here, whoosh, like that. Okay. Now it's been roughly 9 years, because I'm assuming 4.5 years both ways. It's been 9 years, according to us on Earth, how long that twin's gone. So the twin that stayed on Earth might have had a friend up in the green spacecraft, for instance. The friend that stayed on Earth is now 9 years older. So if it was my twin, that friend would be my twin brother would be 59, and I'd still be 50. Okay. Now the twin that actually flew in the orange spacecraft that way, and then the blue spacecraft back, it had a gamma factor for relativity of 2. So its time would be decreased by a factor of 2. So instead of it being 9 years older, my twin brother would now be 4.5 years older. That is not the paradox. That's what a lot of popular magazines say is the paradox. That's not the paradox at all. That's fact. Okay. So when my brother came back, I would be 59 and my brother would be 54.5. Brian's now a little bit younger than I am, even though we were twins born on the same day. Now, where the paradox comes in is when people try to claim, well, wait a second. Since it's the special theory of relativity, isn't motion just relative? Couldn't we just argue that instead of the orange spacecraft flying to Alpha Centauri and back, what if Alpha Centauri just happened to fly to us, the green spacecraft and the Earth, and then turn around and go back? Then in that scenario, the person in the green spacecraft or the person on Earth would have actually aged only 4.5 years, and my brother on the orange spacecraft would actually have aged 9 years. And if that actually happened, if Alpha Centauri really came here and then turned around and came back, then yeah, you would have a valid claim that the other brother should be younger. In other words, I would be the younger one. But you don't have a valid claim because it's clearly obvious which one did it, because there was 2 huge accelerations. When the spacecraft came from here, from Earth into the, or when my brother came from the Earth to the orange spacecraft, that was a huge acceleration. If he had little fuzzy dice hanging from his ears, they would have surely slashed backwards, because it went from 0 miles per hour to 86.6% of the speed of light, and the little fuzzy dice would swing way back here. And then when it got to Alpha Centauri, they would really swing, because they go from 86.6% of the speed of light that way to 86.6% of the speed of light that way, and they would swing really far back that way. And then, of course, when he came back, there would be another one for him dropping down to Earth. But you can't argue that that actually happened, because the fuzzy dice would have given it away. So that's not a paradox, because that other scenario just can't happen where you do it. Now, if the universe were in fact circular, meaning a closed surface, maybe it was a closed surface with a circumference of only 9 light years, then that would be perfect, because then the orange spacecraft could go this way at 86.6% of the speed of light. Let's say the radius was actually 4.2, or excuse me, the circumference was actually we'll say it's 9 light years. Then the spacecraft would come back around. Then you could make the argument, because neither one accelerated, but we don't know that we have a circular universe like that, or a closed universe like that. If that was the case, then that would present a problem. And I think that's a good reason to suspect that our universe is not closed. It's an open universe. So that's 2 of the special relativity ramifications. A third is length contraction. Okay. And that same gamma factor. So if I use 86.6% of the speed of light, then the gamma factor, the thing that changes time or space, is going to be 2. So it turns out that if this spacecraft and this spacecraft were identical, okay, and then all of a sudden the green one is still sitting still, but the orange one's traveling at 86.8% of the speed of light, as it flew by us, anybody on the orange spacecraft walking the distance might say, oh, this is a 100-meter spacecraft, meaning it's 100 meters long. But people on the green spacecraft, in fact, would see it being about 50 meters long, because the gamma factor, again, is 2. Okay, that's called length contraction. and it only contracts parallel to the velocity. So if it's going left to right, it's only this left-right dimension that's going to contract. It's going to actually get smaller from 100 meters long to 50 meters long, but it's still going to be exactly as thick as it is now. So if it was, 10 meters tall, it's still going to be 10 meters tall. That's length contraction, and that's another relativistic fact. We know that's true, and Einstein predicted all of this. Of course, the problem is the gamma factor that I talked about is really heavily dependent on the velocity divided by the speed of light. So if you're talking about speeds that are nowhere near the speed of light, when you divide the velocity by the speed of light, you essentially get zero. Or excuse me, you essentially get zero, because it's like infinity on the bottom of a fraction. So because of that, we couldn't measure it in everyday life. That's why we hadn't noticed it before. Einstein actually predicted it before we ever saw it, and lo and behold, he's right. It does, and we've done serious experiments and seen that the universe behaves that way. One instance is, for instance, a particle called a muon is created in our upper atmosphere due to interacting with our particles in the upper atmosphere, interacting with the solar wind and radiation from the sun. It creates a mu particle, and this mu particle, actually, this muon, has a very finite lifetime. It lives on the order of, say, a microsecond, or it might even be a nanosecond. I can't remember. I'll give you some numbers later about that. But it lives for such a short period of time, that given its speed, there's no way in heck it can reach the surface of the Earth, because traveling, let's say it travels at 86.6% of the speed of light. If that's the case, then it's going to take the distance from the surface of the Earth to where the muon's created. It's going to take that distance divided by 86.6% of the speed of light time for it to get here. And that amount of time is, in fact, longer than the life of the muon. But oddly enough, we detect the muons at the surface all day long, so we know they're actually making it here. Well, how do you make sense of that? Well, if we're looking at the particle and saying, how did the particle make it here? Well, the fact is that it is moving according to us, so its biological, or in this case, mechanical clock runs slowly. So instead of it having a 1.6 microsecond half-life, it actually has a 3.2 microsecond half-life. So it's got plenty of time to make it to the surface of the Earth. So that explains it from our standpoint. But both the muon, let's pretend the muon's, like one of those who's, or Horton Hears a Who, one of those who's living on the muon, those things also have to agree that it hit the surface of the Earth, because that's something that's, we can measure and see that it actually did. So both of them have to agree, and they both have to have a reason for it. Our reason for the muon hitting the surface, as you know, is time dilation. Completely explain the fact that the muon made it here, because it didn't live for 1.6 microseconds. It lived for 3.2 microseconds, because the gamma factor is 2. Can anybody think how the muons would conclude they were able to make it? Because they know their lifetime is 1.6 microseconds, and they know basically that they're going 86.6% of the speed of light. How would they explain the fact that they hit the surface of the Earth? Anyone? We've got 3 effects we've learned about relativity: lack of simultaneity, time dilation, length contraction. I explained why we know the muon makes it is because, according to us, the muon's moving, ergo its time clock is moving more slowly, so it lived for 3.2 seconds instead of 1.6. But according to the muon, it's not moving, so that's not a valid answer. So the who's that live on the muon do not agree that they're moving. So to it can't be time dilation that explains it. Can anybody think now what might explain the fact that the muon hits the surface? That's okay. You guys are newbies. It's not expected, but I just want to give you ample time. So in the muon's frame, the muon's just sitting here, right? It's not doing anything. But this crazy Earth is flying towards it at 86.6% of the speed of light. So the 100-kilometer atmosphere that is the Earth in our frame, in the frame of the muon, is not 100 kilometers. In fact, it's 50 kilometers. So the muon and the who's on the muon say, oh, we hit the surface of the Earth because the Earth was coming towards us at 86.6% of the speed of light. So what would normally have been a 100-kilometer thick chunk of atmosphere we had to fly through turned out to only be a 50-kilometer thick chunk of atmosphere. So we made it easily in our 1.6 microsecond half-life. Any questions on that? Okay, so that's two experiments that could be actually be done and were in some sense done to prove relativity's time dilation and length contraction. Absolutely correct. There's another one, I don't really like teaching it, but most books do, so I will tell you it. They sort of like to picture the mass as if there's a mass and then there's a relativistic mass. And it turns out the formula for time and the formula for mass are identical. So when I say time dilates, meaning a time interval gets bigger for things that are moving with respect to you, they would argue that mass gets bigger when the mass is moving with respect to you. So if a mass of 100 kilograms is moving at 86.6% of the speed of light, to us, we would say, oh, that's a 200 kilogram mass because we see it moving by us, right? And the reason why I do want to bring it up is that's a nice explanation for why things with mass can't go the speed of light. Because if we speed it up to say 86.6% of the speed of light, we would have to use like Newton's second law, which says F equals ma. We'd have to have a force that's able to take that 100 kilograms and accelerate it from 0 to 86.6% of the speed of light. But once we get there, if we're still trying to go to the speed of light, we still need to go from 86.6% of the speed of light to 100% of the speed of light. And in doing so, we're now facing an object that has 200 kilograms of mass. And if we get, say, closer, let's say 90% of the speed of light, now it's going to be even heavier. And then if we get 90%, 95% of the speed of light, it's going to be heavier still. And in fact, it asymptotically approaches infinity as you get to the speed of light. So the only way that anything with mass could reach the speed of light is with by supplying an infinite amount of energy or even an infinite amount of force. So that's the advantage of thinking about relativistic mass. Most of us purists see mass as a scalar, and therefore a scalar can't change like that. That's why we don't like teaching it, because it's not in some sense fundamentally correct. But there is an effect that is consistent with mass increasing. So I'll let you know that, yes, the faster you go, you can sort of imagine that the mass is getting bigger, so it's going to take even more force and more energy to get it to go faster. So that's it. That's all I wanted to give you for special relativity. That was published in 1905. Einstein published in, I think it was 1911. He published his general theory of relativity. So it took him about, another 6 years to figure that out. But luckily, when he published that, luckily when he published that, the eclipse that was going on was sort of interrupted, if you will, by something called World War I. So the experimental devices that went out to measure the aberration of starlight ended up failing to do the observation due to some of them were captured, some cannibals caught some of them, others were caught by military, some had bad weather. But that was lucky for Einstein, because it turned out he had forgot to carry the 1, so he's off by a little bit, and he made a correction to his calculation in that intervening period. So by 1915, when he actually had the observation made at the next eclipse, he was right on the money, and he became famous the next day. And all that changed with the special theory of relativity to the general theory of relativity is they took out that word inertial. So the laws of physics are the same for all observers, period. That's the general theory of relativity, principle 1. The other principle is called the equivalence principle, which just says there's no experiment you can do on a small scale that differentiates between an object accelerating upward, say at 9.8 meters per second, and an object sitting in a gravitational field that has a gravitational acceleration of 9.8 meters per second. So with that equivalence principle, Einstein was able to make the equations of general relativity. He had to use tensors to do it, because tensors are the language of conversions between different coordinate systems, whether they're moving or not. And by using tensors, the laws of physics, when you write them, will be valid in every reference frame, because there's a distinct formula that applies when you translate a tensor coordinate system from one frame to another. So that's basically it. And I'll talk more detail about general relativity next time, but I'm letting you guys go. Like I said, I'm going to let you go a little bit early. Everyone's free to go. You're also free to stick around if you have any questions. And I will see you all next week. Start on your practice test, get your homework done, all that good stuff. Oh, don't forget to do your lab either. Thank you for coming. What'd you think of that, Autumn?
Ice cream. I took nothing but ice cream out of that. Just
Uh,
all ice cream.
well, that's not a good deal.
You're just like, oh, we're gonna take this ice cream ship, and then we're gonna go to this ice cream ship, and
Millions of ice creams. Millions and millions
then
of
we're
ice
just
creams.
gonna have nothing but ice cream. I'm sorry, but your ice cream melted. Your brother is melted.
Everything's
He
ice
is
cream and it all
gone.
melted.
He is gone.
Yeah, that is a downfall.
there
But
there is no more ship. You ate it because you're hungry.
what makes you feel any better? The ice cream got thinner, not shorter.
That means your mind thinks that there's less, so you'll eat more.
Mm-hmm.
And so when you see less, you tend to indulge a little bit more.
Exactly. We got to buy small dinner plates, and then I can lose weight.
The more you fill up your plate, I mean, if you're given a huge plate, you're gonna fill it up.
Yep. And I'm gonna go back for seconds and thirds.
No, yeah.
All right. Well, I've got a former dean that's getting ready to retire, or he's retiring, and we're throwing him a party today. So I got
Returning or retiring?
retiring. Sorry. So he's retiring. That's a bummer. I really liked him. He's an awesome dean. I'm gonna go
Well,
to his going away party
on
and
Zoom.
all that good stuff. No, actually, we're having it at the campus,
Oh
but
man, you're gonna
we're
drive all the way to
following our
campus?
6 foot guidelines and wearing masks and all that good stuff.
Oh, have fun with your drive back to campus.
Yeah, I can't believe I got to go all the way to work. Got to drive all the way to work.
Seriously, man.
Yeah, I'm not used to doing that, but as a practice run, I went to Olive Garden yesterday, so I think I can pull it off.
Summer is going to be back in classes, is it not?
A lot of people are. My department did not choose to do that for the summer because we have such a light load anyways, and we're not doing the summer with any kind of contact. I might actually be coming in a lot more often just so I can do some more experiments and getting bored with the same ones.
Oh, well,
But
yeah.
the fall is when we're actually going to try to bring, and we're trying to do it all, have everybody here. But we might have to make special arrangements for students that have not yet been vaccinated and maybe are worried about coming. So we're going to have to.
Telling you, man, that vaccination, my vaccination on Monday, oh,
You
I
said you
was,
felt bad.
I felt horrible. And that was the
Yeah,
first one.
that's not good. That's a bummer. Well,
My
you might
head
have actually
was
had it.
racing.
They're saying that usually when you've already had it and then you get the vaccine, you feel a little worse from the
No,
vaccine than when you didn't. But it's not a done deal. It's just
I think I was on antibiotics for my teeth, and apparently they said you could feel it a little bit worse when you're on antibiotics.
oh, gotcha. That would
So
make some sense.
I'm just like, oh my god, this sucked. Right
Yay! I'm
now,
so
just my
glad.
joints hurt. I feel like I have arthritis in my hands.
That stinks.
All right, I'm gonna let you go because you've got to drive, and
All right. Well, you have a good one, Autumn, and thanks for letting the class know I was running a little late.
it's fine. It's fine.
See ya.
I'll see you later.
Bye bye.